Okay, so we will be doing optimality conditions today uh, for constrained optimizations. And so this is the constrained optimization problem, the generic form that we shall be using in this course. So minimization of this function f of x, which is a mapping from n dimensions to a scalar, subject to gi of x less than equal to 0. I is the set of inequality constraints, and aj of x is equal to 0. Script E is the set of equality constraints. And so in vector form, this will be minimize f of x subject to, now we have a vector function here, g of x is less than equal to 0, and h of x is equal to 0. Where G is a mapping from n dimensions to L dimensions, where L is the cardinality of the set of inequality constraints, and H is a mapping from n dimensions to m dimensions, where m is the cardinality of the set of equality constraints. And we have defined the feasible set f, script f equals the set of all points x such that for all inequality constraint, gi of x must be less than equal to 0. And for all j in the set of equality constraints, j of x must be equal to 0. So this is the feasible set. If we are trying to maximize a function, then we can easily replace f of x with negative f of x to convert it to this form. If we have a greater than or equal to constraint like this, then we can replace gi with negative of gi, and then it becomes a less than equal to constraint. Okay, now active versus inactive constraints. Okay, now these are the inequality constraints. gi less than equal to 0. Now, for some x, okay, gi of x may be strictly less than 0, or gi of x may be equal to 0, right? When gi of x is strictly less than 0, then the constraint is inactive. And if gi of x is equal to 0, then the constraint is active. That means it's in the boundary of the feasible region. Okay, equality constraints are considered to be always active. So the active set, given any x, the active set is I belongs to inequality constraint, g of ix is equal to 0, union set of equality constraints. So this is the active set. Okay, this is something that's very relevant to us in this lecture. There'll be a strong distinction between gi of x is strictly less than 0, which is an inactive constraint, and gi of x equals 0, which is an active constraint. Okay, so let's look further. So a regular point, x star, if the gradients of the active inequality and equality constraints are linearly independent. So for each of these gi of x, we have a gradient, right? Oops. So these are all the active constraints. I belongs to the inequality constraint intersection with active constraints. So all the active inequality constraints, their gradients, and the gradients of all the equality constraints, because equality constraints are all active, right? So all these gradients, if we take their transposes, and each of those becomes a row, then this matrix should have full row rank. That makes x star a regular point. Lagrange function, okay, the Lagrangian. So minimization with respect to x, f of x, and these are the inequality and equality constraints. The Lagrangian is Lx lambda mu, which is f of x plus summation for the inequality constraints, lambda I gi of x plus summation j for the equality constraints, mu j hj of x, and lambda I should be greater than or equal to 0. This is the vector form, and the Lagrangian in vector form is Lx lambda mu equals fx plus lambda transpose gx plus mu transpose hx. Okay, now constrained minimum. Let's define a local minimum. X star belongs to f, so x, we have a point, this point here, that's in the feasible region, and it's a local minimum if there exists a ball. Okay, if there exists a ball, so this is the feasible set, and x star is in the feasible set, feasible region, and if there exists a ball of finite radius r centered around x star, such that for all x, take any x, belongs to the ball intersection feasible region. So this is the intersection. This is the ball. The blue circle here is the ball. And this yellow region is the feasible region. And so its intersection is the overlapping region here. Everywhere in this overlapping region, take any point x, okay, then f of x star must be less than or equal to f of x. So f of x star, everywhere in this overlapping region, f of x star is the minimum you can get. Okay, that's the definition of a local minimum for a constrained optimization problem. It's a strict local minimum if we replace this less than equal to with strictly less than. Otherwise, the definition remains the same. X should not be equal to x star. I should have put that constraint here, condition here too. X should not be equal to x star. Now, if x star everywhere in F, everywhere in the feasible region, f of x star is less than or equal to f of x. No ball, everywhere in the feasible region. If this holds, fx star is less than or equal to f of x for any x in this feasible region, then x star is a global minimum. Okay, now let's look at the conditions for a local minimum. Okay. Primal and dual feasibility conditions. So this is the primal constraint optimization problem. Okay, now this is the Lagrangian, fx plus lambda transpose g plus mu transpose h, and lambda must be greater than or equal to 0. Stationary point, x star, lambda star, mu star, assume some constraint qualifications hold. I'll get to that later. Actually, did I already tell you about Slater's conditions? I think I might have, but so we have primal feasibility, g of x star less than or equal to 0, h of x star equals 0. These are the same as this. So this is a stationary point, x star, lambda star, mu star. Okay, and this, for this x star, it must be feasible. In other words, g of x star should be less than or equal to 0, and h of x star should be equal to 0. This is primal feasibility. The point x star should satisfy the feasibility constraints. The dual feasibility condition is lambda star should be greater than or equal to 0. Then we have the complementary slackness and stationary conditions. The complementary slackness condition is this: lambda star transpose G of X star must be equal to 0. In other words, in terms of scalars, summation I, lambda I star Gi of X star must be equal to 0. Okay? Now, each term in the summation, Gi of X star is, we're in the feasible region, right? Since the primal feasibility conditions hold. So G of X star is less than or equal to 0. Okay, so Gi of X star is less than or equal to 0. And lambda I is greater than or equal to 0. So what can you say about each term, lambda I star Gi of X star? The two factors, lambda and G, are of opposite signs. This is less than or equal to 0, and this is greater than or equal to 0. So the product must be less than or equal to 0, right? Now, when I say that this summation, lambda I star Gi star, Gi of X star is equal to 0, now each term is less than or equal to 0. So when will their summation be equal to 0? When each term separately is equal to 0. So for each I, lambda I star Gi of X star must be equal to 0. Correct? Only then will the summation be equal to 0. Since no term in the lambda I star Gi of X star in the summation is positive, if the summation is 0, each term lambda I star Gi of X star must be 0. That's what I said, right? Lambda I star Gi of X star is less than or equal to 0. The stationary condition. Yes? Any questions? The stationary condition is this: derivative of the Lagrangian with respect to X must be equal to 0. In other words, del of f of X star plus lambda, summation lambda I del of Gi of X star plus summation j mu j del J of X star is equal to 0. So this must be 0. Okay, now how to express this in vector form? This, in vector form, is this. Now, we've seen what gradients are. For a scalar function, we know what a gradient is. We also know what's the Hessian, right? The second derivative of a scalar function like Gi or Hj is a second derivative is the Hessian, and the first derivative is a vector called the gradient. Now, when we are looking at vector functions, bold G and bold H, their derivatives will be matrices called the Jacobian matrix. Okay, and so this is how we express the stationary condition in vector form. So this del X, so these are the Jacobians of G and H. So what is the Jacobian? So we have a vector function, f of x, which is f1 of x, f2 of x, and fn of x. So f is a mapping from n dimensions, x is n dimensions, n as in Nebraska, and f maps these n dimensions to m as in Missouri, number of dimensions, m. Okay, that's why we have f1 through fn. And del fi for each of these scalar, del f of I of x is, we know this. Right? We take the derivative with respect to x1, with respect to x2, all the way until with del fi with, over del x sub n. So this is an n-dimensional vector, right? The gradient of each scalar function fi is this, which is n dimensions. Now for the vector function, the derivative of this vector function is like this. Basically, we take the gradient with respect to f1, and that becomes one column. We take the gradient with respect to f2, that becomes the second column, not shown here, all the way to the gradient with respect to the last scalar function here, fm. So del of that becomes the last column. So this is, see, how many rows do we have? X1 through xn, right? So we have n as in Nebraska rows, n. And how many columns do we have? So we have f1, then f2 in the second column, all the way to fm in the mth column. So we have m as in Missouri, different columns. N by m. Okay, this is del f of x. Now, how do we differentiate A transpose f of x? Okay, where A is a constant vector. So this is x, n-dimensional. A is m-dimensional, and so is f of x. So these are both m-dimensional. And this x is of a different number of dimensions, n. A transpose f of x is this. I equals 1 through m of summation ai fi of x. And now the Jacobian is this. Del f of x is, the Jacobian of f of x is this. Correct? And we are, so how do we differentiate this A transpose f of x? Del of A transpose f of x, I'm differentiating the scalar. A transpose f of x is a scalar now, is equal to summation ai del f I of x, which is del the Jacobian matrix times A vector. Okay. Jacobian times A. So del of A transpose f of x is del f of x times A. This is the Jacobian matrix of f vector function. Okay. So this expression I'll be using. This is the del fi of x. I don't know why this is spotted now. So remember this expression. Now, the first order KKT conditions. Kuhn-Tucker conditions, KKT conditions for optimality. Okay, so this is the constraint optimization problem. And this is the Lagrangian. Primal feasibilities will hold at if g of x star is less than or equal to 0, h of x star equals 0. Dual feasibility implies that lambda star should be greater than or equal to 0. Okay, and complementary slackness condition says that lambda star transpose g of x equals 0. The stationary condition is this in vector form: del x of f of x plus Jacobian of g times lambda star plus Jacobian of h times mu star must be equal to 0. Okay, so this is the stationary condition expressed vectorially. And what I did was, I just differentiating this. Remember the previous slide? This derivative of this A transpose F equals del FA. That's the same expression I'm applying here. Derivative of lambda transpose G equals Jacobian of G times lambda. Likewise for the third term. Mu transpose H, derivative of that is Jacobian of H times mu star. And that must be equal to 0. So these are the first order KKT conditions for optimality. Okay, theorem. If the regular point x star is a constrained local minimum of the COP, the constraint optimization problem, then there exists unique Lagrangian multipliers, lambda star and mu star, satisfying the first order KKT conditions. Okay? So if x star is a regular point, which means that, del x, this is a vector, right? So for each of the active constraints, the derivatives are all linearly independent. Okay, and you'll see that graphically. And so then there exists such lambda star and mu star satisfying the first order these conditions, first order KKT conditions. This is an important theorem, and we shall illustrate this graphically. And these are the KKT conditions. And you always try to memorize the KKT conditions. When you solve problems, it will gradually be embedded in your memories. Now we have second order KKT conditions too. If there exist unique Lagrange multipliers lambda star and mu star satisfying the first and second order KKT conditions, then the regular point x star is a constrained local minimum of the constraint optimization problem. So these are the second order KKT conditions. The second derivative must be positive semi-definite, okay, of the Lagrangian. And these are analogous to unconstrained optimization. In the unconstrained optimization problem, you don't have g and h. So this would simply be the function f of x, right? And the Hessian of the function must be positive semi-definite for it to be a local minimum. And now for a constrained optimization problem, with the constraints, instead of the objective function, we have the entire Lagrangian, and this its Hessian must be positive semi-definite. So this is another important theorem, and this is the set of second order KKT conditions. Actually, only this. And we will try to explain all these graphically now. So we have a function f of x here, and we're trying to minimize the function. Now, let's say x star is our solution. The global minimum is this. And these are contours of fx equals constant. Okay. Here, fx is the minimum. As we go further away from this global minimum, the value of f increases, correct? So the value of the function along this contour, let's say is 2. Here it will be 3. In this contour, it will be 4. These are the level sets. Now, let's say this is the constrained minimum. This is the unconstrained minimum, and this is the constrained minimum. Now, at this x star, the gradient must be pointing in the outward direction, in the direction of increasing values of the function, right? The gradient is the direction of steepest increase of the function. And it's also orthogonal to this f of x equals constant, this contour here. Agreed? So this is the unconstrained minimum, and these are the level sets. And so this is subject to x belongs to f. So we have to be within the feasible region, and this is the constrained minimum. X star equals argument f of x, where x must belong to the feasible region. Yeah, you had a question? Mama? Okay. So the gradient of the objective function, which is this, L f of x star, points away from the global minimum. It points in the direction of increase, right? Therefore, since this is the global minimum, it's pointing in the opposite direction. Are you guys with me so far?
Yes.
Yes.
And the second observation is So this is f of x equals constant, and this is del of f of x, and they are orthogonal. Okay, so this direction, the gradient direction, is orthogonal to this curve here. F of x equals constant. Now, let's say we have an equality constraint. Okay, all we have is an equality constraint, a single equality constraint, h of x equals 0. So this is our constraint optimization problem. F of x, and we are looking at just a single equality constraint. Okay, so x star, if it's feasible, then h of x star must be equal to 0. Okay, this is this, you see this red line here? This is where h of x equals 0. And only this red line is feasible. And everything on this side and this side is infeasible. Only the red line is feasible. Okay. Now, so this is the feasible region. Hx is equal to 0. Now, look at the gradient of h of x, del h of x. This is del f of x star. This red arrow is del h of x star. Okay, and this gradient can be in this direction or in this direction. This. Okay, now look at this. Del h of x star is pointing in this direction. Why? Because look here, h of x is greater than 0 here, let's assume, and h of x is less than 0 here. And since del h will point in the direction of maximum increase, it will be orthogonal to this feasible region, and it will be pointing in this direction because it's increasing here, right? It's positive on this side. On the other hand, if I change the greater than and less than, in this case, del h of x is pointing in this direction of increasing h. Correct? Are you guys with me so far?
Yes.
Okay, so del h of x is in this direction or this direction. Now, it must be orthogonal to h of x equals 0. So this red arrow must be orthogonal to this h of x equals 0 curve, this curve, hx equals 0, correct? Because it must be orthogonal, right? So, at x star, the feasible region hx equals 0 must be tangential to the level set of f of x. Now, you see this. This is a level set. F of x equals some constant. And this is h of x equals 0. Now, these two are touching each other at this point, x star. Okay. They're touching each other. So in other words, the two curves are tangents. If these two curves are tangents, and since their dels, their gradients are orthogonal to these two curves, the gradients must be, see, these are the two curves I'm talking about, tangent curves, okay? These two curves are tangent to one another. So now why must they be, why is this x star? Suppose we move in this direction. What will happen to, well, we're moving along the feasible, we're still in the feasible region. As long as we stay in this red path, we are feasible. Okay, so this point is feasible, but what's happening to the value of the objective function, f of x, as we move this way? You look at these contours, the level sets, right? It's increasing, right? F of x is increasing, right?
Yeah.
We're moving away from this global minimum. In this direction too, this is feasible, but we are moving away from the global minimum. So we are increasing in this direction. Okay, as we move away in the feasible region, as we if we move away from this tangential point x star, then we are increasing the value of the objective function, which we don't want. We want to minimize the function. Okay, now again, this is the feasible region, and level sets of f of x are tangent at x star. Okay, now suppose we move. Another point. But if we move in any other direction here or here, we will be infeasible. We have to stay in the feasible region, right? So these are the only two possible cases. So we can see that in this case, h of x less than 0 here, h of x greater than equal to 0. This was the direction of del of h, the gradient of h. This was the direction of the gradient of f of x, the objective. And since these two curves are tangents, these two are in opposite directions. Correct? So they're in opposite directions now, in this case. And or they can be in same directions. If I were to swap this greater than and less than sign, then this arrow would get rotated by 180 degrees, so it will be along del f of x. Correct?
I have a question, Dr.
Sure.
Das. So if we swap those inequality signs, would we still get x star as the minimum?
Yeah, h of x equals 0 is the minimum. Both sides are infeasible. Instead of h of x equals 0, we can replace h of x with minus h of x equals 0.
Okay.
Right? But this red curve is still the feasible region. So this will still be the constraint.
Yes.
Okay. So the gradients of the objective function and the constraint are either in opposite direction or in the same direction. In this case, they're in opposite directions. Okay. Now, since they're in opposite directions, what we can do is, so sine of del f of x, oh, well, this is a little confusing, ignore it, it's for each direction. So del f of x, there must be some mu star, okay? In this case, there is some mu star, they're in opposite directions, right? So if we multiply this del h with some mu star, okay, then it will be of the same magnitude as del f of x, correct? So
Yes.
if you add the two, they will cancel out. They're in opposite directions, and if you scale this properly with this mu star, then they will cancel out. For some mu star, del of x star plus mu star del of h star equals 0. Right?
Yes.
And furthermore, this mu star has to be greater than 0 in this case, because the red arrow and blue arrow are in opposite directions. Okay, now, on the other hand, if this were the situation, this side were greater than equal to 0, this side were h of x is less than 0, so the gradient of h is now pointing in the same direction as the gradient of f. The red arrow and blue arrow point in the same direction. So in this case, we can scale this with some mu star, but mu star must be negative, right? Then they will cancel out.
Yes.
Right? So mu star in this case is negative. For some mu star, this will cancel out. Okay, and so mu star in this case was positive, in this case was negative. But some mu star, which can be positive or negative, exists at this point, x star. Okay, such that this del f of x star plus mu star del of x star equals 0. Are we good with this?
Yes.
Okay, now let's look at inequality constraint. So this is the stationary condition. Okay, so del f plus mu star del h equals 0, and mu star can be less than or greater than 0. Okay, now let's look at inequality constraints. Okay, now g of x is less than equal to 0. So this orange shaded region is my entire feasible region now. This is g of x less than 0. Everywhere here is feasible. And this is g of x greater than 0. And this red curve here is g of x is equal to 0. This guy here. Okay? And so now this is x star, the constrained optimum. Now here, as before, this is the feasible region. Now this is the unconstrained minimum. Okay. Now what happens here? This is the constrained minimum. First question, is del g of x star active or is g of x less than equal to 0 an active constraint or inactive constraint? Here, it's an active constraint. Okay, an active constraint is something that's borderline on being being violated. Okay, so this is the active constraint. If you perturb this by an infinitesimal amount in this direction, then you get to the infeasible region. Okay, so this is an active constraint. Since x star equals 0, the constraint is active. Okay, now if we stay in the active region, if we move further away, what happens to the function f of x? If we move this way,
Increases.
it increases because we are, if you follow the level sets, these blue contours, right? Okay, we are still in the feasible region, but f of x increases. If we go in this direction, f of x increases, but although here the constraint is active, here again the constraint is active, but if we go along this direction, along this g of x equals 0, again the function increases, right? That's why this x star, where this feasible region and this contour, they are touching each other, that's the point where x star occurs. Okay, now this g of x equals 0 must be tangential to this level set of f of x, correct? As before?
Yes.
Yes.
And this is the direction of the gradient. The direction of the gradient has to be opposite of the gradient of the objective function. Del G and del F must be in opposite directions because this G of X is less than equal to 0, which means that only this side is feasible and this side is infeasible. So if this is feasible, G of X is less than 0, and in an infeasible region, G of X is greater than 0. So this is the direction of increase. Here, from here, this is the direction of increase of G of X. And this is where G of X becomes more and more negative. Okay, from here, if we move this way, g of x increases, becomes positive. Here gx equals 0. If we move this way, g of x decreases. Okay, so the gradient of g, del g, must be facing in this direction, this red direction, and that is always opposite of the gradient of f. Are you guys with me? They're not, they can never be in the same direction.
Yes.
They must be in the opposite direction. Okay, which means that if you scale this with, there must be some scalar, lambda star, such that if you scale this, multiply this with lambda star, the length become equal, but they're in opposite direction. It will then del f plus lambda star del g will be equal to 0, correct? But
Yeah.
what will lambda star be in this case? It must be positive, right? Because they're already canceling out in opposite directions.
Right.
The lambda star must be greater than 0. And here, g of x is equal to 0. Remember, lambda is greater than 0. G of x is equal to 0. Okay, so I'm repeating this again. G is an equal to 0, so it's an active constraint. G is 0, lambda is greater than 0. Now we'll see if G is less than 0, then lambda will be equal to 0. Okay, and that will reason that. Okay, so lambda and G are of opposite signs. Well, now one of them has to be equal to 0, but not both. Only one of them has to be equal to 0. Okay, so here, this is our stationary condition. Del f x star plus lambda star del g of x star equals 0, and lambda star is greater than 0. This x star, at this x star, g of x equals 0, so this is an active constraint. Now, complementary slackness for the active constraint. Each of these terms has to be equal to 0, right? And when we were doing constraint optimization, the stationary conditions, if you go back to the stationary conditions, what I had said then was, oh, so far back, I didn't realize otherwise. So each of these would be equal to 0, right? Each term in the summation would be equal to 0. Okay, either lambda I star would be equal to 0 or gi of x star equals 0. So we just looked at the case where gi of x star equals 0 and lambda I of x star was, sorry, lambda I of I star was greater than 0, strictly greater than 0. Okay. So this is where we were. Okay, and this was, so the constraint is active. For the active constraint, gxi equals 0, the corresponding lambda dual variable is strictly greater than 0. Now, let's look at another case. Now, let's say the global minimum is in fact the constraint minimum. So this is the feasible region now. The global minimum is this. It lies in the feasible region. Okay. So you see this, the feasible region now has shifted this way. Okay. So it's feasible. Now here, since it's inside, okay. Now since this is the global minimum, its derivative must be equal to 0. Del of f must be equal to 0. Correct?
Yes.
This is equal to 0, right? Now, So the unconstrained minimum is also the constrained minimum in this case. So x star argmin f of x belongs to the feasible region. Now, what happens to del G now? All right, what's the value of G in this case? It's inside this, right? The value of G is strictly less than 0.
Yeah.
Right? So G of x is strictly less than 0. And so del G, well, it will be in this direction, some direction. Okay. Now del F equals 0. Now, and del G will be some value. Now, del F plus 0 times del G will be equal to 0. If we set lambda star to 0, since del F is already equal to 0, this whole thing will be equal to 0. Correct? So here we are looking at the situation where the constraint is inactive. It's less than 0. In this case, the Lagrange multiplier lambda star is equal to 0. So for an inactive constraint, the Lagrange multiplier will be equal to 0. On the other hand, for an active constraint, the Lagrange multiplier will be strictly greater than 0. Okay. Did you guys understand this part?
Yes.
Now, again, you see that this is the stationary condition. Okay, so del f of x star plus lambda star del g of x star equals 0. So the stationary condition is this, and that's being met. And again, the complementary slackness condition, g of x star is less than 0, lambda star is equal to 0. So when you multiply lambda star with g of x star, you get 0. Oops. Sorry, this got messed up. But anyways, this is the optimization problem. And this is the Lagrangian. These are the 4 KKT, first order KKT condition, and this is the second order KKT condition. Okay, and this summarizes everything. Now, okay, now what if we have this situation, g of x greater than or equal to 0? Then we can either put a negative sign here in the Lagrangian, or we can we can do this, or we can the other alternative is to make this dual feasibility be lambda star less than or equal to 0. I prefer this. If the constraint is greater than or equal to, I prefer to put a negative sign there. Now, if it were a maximization problem, then this is the second order condition, negative semi-definite. And we put a negative sign here too. Now, solved examples I'll do in the tutorial. Okay.
Hello, Dr. Das, I have a question. Hello.
Yeah.
So here, are we considering the objective function and the constants to be convex, or it will work?
That's a very good point. I will cover that in the next lecture.
Okay. Yeah. That will be good. Yes. Thank you.
Okay, so see you guys in the next meeting then.
Thank you.